SwayamPrabha. Digital India. Educated India.
So in the last class, we are looking at sampling and this application of the sampling theorem. Okay, so the sampling we saw two aspects. Like one is the sampling theorem itself, and other one is about the reconstruction. Okay. So ideal reconstruction will be Shannon reconstruction, and then this sampling theorem itself. Okay, that the signal needs to be sampled at least twice its frequency contents to get it to the final form, which digital form, which is representing the original signal content. If it is not done, then the signal contents are all lost. Ideally, we will need about 3 to 4 times the sampling frequency to really represent in the practical case scenario. So now we began with further to this, we began with the digitization of a system. So what it means is, when you sample a system, you represent them as these kind of dot samples that are sample points that are represented here. Let me get the mouse right. And these samples are held constant over the sampling period, which is t. Now, if this kind of output or input goes to the actuator or your plant, how the plant behaves is what we discussed in the digitization. That is what will happen when the system is digitized, or if you want to mathematically represent this continuous system, which is like getting this kind of a input, which is steppy kind of a form of input, this kind of a steppy form with this value held constant over the time interval, then what is its effect on a system? That is what we started studying. Okay, and to that effect, we saw that for any continuous domain system, this is a solution of a system. This is a system of the kind x dot is equal to ax plus bu, and this is solution. Okay, the solution has two parts. One is like a homogeneous integral, a homogeneous solution, and other is a particular integral part. Okay, now we apply this solution between the two time instances, where we start off with time instance k times capital T. Capital T is the sampling time, and we predict the state at k plus 1 times t. Okay, so within this time, the system will progress within this time interval k plus 1 t to kt to k plus 1 t, which is the time interval of capital T, and there we will get this contribution of the homogeneous part of the solution, and then this is particular integral part of the solution. Now notice here, we integrate not from 0 to t, but now since we are starting at kt, this will be kt to k plus 1 t, and this 0 state here is x of kt. And similarly, you will find that this final time is k plus 1 t, and then tau remains as it is because it's an integral variable, and then all these terms remain the same. And then we shift the time to this time variable or tau variable defined in some different way, shifted way, and then we simplify these to get it to this final form. So x of k plus 1 now is e to the power at. Okay, A is the system matrix for the original analog system. X dot is equal to x plus bu kind of a system, and capital T is your sampling time. Okay, x of t k, I mean the e to the power at times x of k, and then integral 0 to t e to the power as b times ds. So this is how you get these two kind of matrices which are independent of state. Okay, there is no x coming in this at all. So these are like system characteristics matrices then. Okay, these characteristics will depend upon matrix A and the sampling time that you have used, the sampling time t. Okay, so with this we have now the system coming in this form. X of k plus 1 is equal to phi of t x of k plus psi of u of k. Okay, psi times u of k. Okay, this phi is this e to the power at matrix, and psi is integral of e to the power as ds, b ds. Okay, so as or like b is not a function of s, so we can come out of the integral, and this is integral of this matrix, definite integral 0 to t, and multiplied with the vector b, which is a system input vector, and y of k is equal to c times x of k. That remains as it is. And now one can iterate this further, like say x of say we start at same state k0, then k0 plus 1, x of k0 plus 1 will be x phi xk 0 plus psi u k0. Then x of k0 plus 2 will be similar way, and we substitute for phi of x of k0 plus 1 here, and like you get this again, like this kind of a function here, and you collect these terms in general for starting from k0. Okay, so k0 is equal to 0 to k, so this will become some kind of a summation. Now you see this power here, this is pi square coming here, or like k0 plus 2 kind of a thing, and that's how like this will become now. You just see this carefully. For each term there will be now higher and higher powers that will be coming up for phi and psi here. Okay, so you can see this phi square x of k0 and phi times psi u of k0 is coming. Okay, and if you have this k0 state, the initial kind of a state of a system to be 0. Okay, so we consider many times for a transfer function also 0 initial conditions. Then like this will be just in terms of u of k. So this expression assumes that there is a 0 initial condition. Okay, otherwise this term phi raised to k minus 1 times x of k0 would be additional term that will be coming here. Okay, so now let's what is the significance of this is that like we can get a state x of k given u and this matrices alone. Okay, so this matrix phi and psi are known. Then based on that, those matrices we can get the response of the system to any input, in general any input u. Okay, now all of this is now happening in the digital domain form. Okay, so we are getting this kind of a discrete values of the state vector at every time instance, or like this sampling time index, which is k. Yeah. So this is how the system response will come out. And if you see this carefully, this is similar to what we have as a convolution in the discrete domain, in the continuous domain. So this is a convolution in the discrete domain, similar to convolution in the continuous domain. So this part here, if you see, has k minus j kind of a, or k minus 1 minus j kind of a form, and this is a j form. Okay, so j and k minus j kind of forms are there. Okay, so with this one can predict what is this function with which input is convolved to get your final output. So the same way we have convolution in the analog domain, you can see the convolution in the discrete domain, and then the function that is convolved with becomes like a impulse response of that system. So in the discrete case, it is called a pulse transfer function, okay, or pulse response function, not transfer function, pulse response function, okay. So if you see this in the convolution kind of a way, you can see that c times phi raised to, this is our new variable L minus 1 psi, okay, this function, okay, is pulse response function, okay. So this is like a input u of j convolved with h of L, which is impulse or pulse response function. Then you get your output y of t, okay. There's one kind of a concept here. Now further to that, now we seek now a way to get some kind of a transfer function in the digital domain. Now to get that, we need to like define some new quantities, okay. So we'll come to that. So to get our transfer function, so we define this operator q, okay, which is called pulse transfer operator, okay, in such a way that when the q operates on some x of k, then it shifts the state by one sampling instance, okay. So q square x of k will be x of k plus 2, like that, okay. So q is like some kind of operator which we have defined now to get some kind of a forms for the transfer function, and we get now the way we get things in the continuous domain in terms of the variable s, which is a Laplace variable, Laplace domain variable s. We now get this equations or like the transfer functions in this operator, okay, in the operator variable, okay, q. Okay, so if you now see again our previous system, okay, we had x of k plus 1 is equal to, this was our derived equation previously, okay. If you see these two steps back, we had this equation, x of k plus 1 is equal to phi of t x of k psi of uk, okay. So this equation now can be written in the form of this operator, okay. So q times x of k will be equal to all these things. So if you combine terms with x, like x of k together, then qi minus phi, okay, times x of k will be equal to psi of uk, and then this inverse times, like you get this. Now we know the output is y of k is equal to c times x of k, okay. So you substitute for this x of k here, and you get this as the output. So now this becomes like input output relationship, okay. And if we define the transfer function as a ratio of y of k over u of k, then what we get on this side here is a transfer function, okay, in terms of this new operator q. So this is a transfer function of a digital domain system. So this is how we start getting now the similar kind of analogies which we have in the similar to what we have in the continuous domain, okay. So one can see that, look, how we suppose we have the system x dot is equal to x plus pu and y is equal to cx. From there we can get to this kind of a transfer function h of q, basically using phi, which is equal to e to the power a t, where t is a transfer function and where t is a sampling time, and psi is like integral of e to the power phi s, so that's the integral of this term. Okay, so this A times B, like that B matrix is coming here, and A matrix is coming here, and C matrix is here, like that. We have used all these three ABC matrices to get to the final transfer function, okay, in the digital domain. Okay, so this is how we proceed to get the transfer function in the digital domain, and these transfer function can then have definitions of poles and zeros and all those stability conditions will come up. Okay, so we'll not get into those details right now. What we'll focus on is now how do we use this as in the application of filters. Okay. So this is one of the ways one can see that the continuous domain system can be converted into a digital domain system. Okay, and the issue remains like, okay, how do we implement such a system? Or suppose we have defined now, say last class we saw that, okay, filter is nothing but some kind of a transfer function through which, like, when the input is passed, then some output will be produced, which is can be seen as a filtered output. So similar way, we have this digital domain transfer function. We pass some input to this function, and then, like, this may act as a filter also. Okay, so you can define this system to be a filter, like, x dot is equal to x plus bu can be your filter, which will have some certain kind of a form of matrix A and B, and one can now look at this as a filter transfer function. Okay, so we'll see how this can be used in actual implementation of a filter. We'll look at that. So we need to kind of have a sense of this shift operator clear here. Okay, shift operator here, and like this is same kind of a operation that happens with the definition of Z transforms. Okay, so we'll not get into too much of a Z transform domain things. I mean, there is formal definition, mathematical definition of Z transform, and there are some certain conditions under which the system can be transformed from the discrete kind of a form to Z domain. Okay, and get like a lot of these details of, like, the digital domain system will appear there also. So this using pulse transfer function, pulse transfer operator is one way of converting system from continuous domain to digital domain, and Z transforms will be another way to do that. Okay, there are some subtle differences, although, like, this property is same for both the operators. There are certain differences between the two, which we will not get into right now. Okay, for practical purposes they are not really so important. Okay, so as far as possible, we'll prefer to kind of use the system with this kind of a pulse transfer operator, because it has some kind of a good physical sense of what is happening in the actual practice. Okay, that is getting reflected in this in a very neat way. Okay, which may not happen with the Z transforms. Okay, so is one part that is what we observe here, and we from here we'll just move on to some filters and its implementation. Okay, so this is a transfer function, and then we'll skip this part of the Z transforms, and we'll go to the filters eventually. Okay, so you can, these are like mainly mathematical kind of definitions, and it gives some kind of a properties which are similar to Q operator properties. Okay, but not exactly the same. Okay, so that's what we will see. Okay, now we get to some kind of a fundamentals of a filter. So the system to transform from one domain to other domain. Okay, so now we are using this Z as similar to, like, Q operator. We use this something called bilinear transformation. Okay, where it pops up from is basically if you see the eigenvalues of this is coming from how the poles get mapped. Okay, so the bilinear we'll see what is this bilinear transformation. We'll come to that in a while. But one can see now that there are these different domains. There you started off with this differential equation, then you convert it into state space form, or you can convert it into transfer function, or you can have a discrete domain transfer function with the shift operator q, or you can have discrete domain transfer function with z transforms, or using these bilinear transforms. Okay, so see, you can either use this discrete domain transfer function with the shift operator q, or using this bilinear transform. These are the two ways we can convert the S domain system to Z domain, okay, or to discrete domain. And so discrete domain, discrete time relationship between yk and uk would be that what we derived with the shift operator. Okay, so there are different kinds of domains of operation that we can see here. Let's talk a little bit about a simplified way of doing the thing with this, the bilinear transform way of doing things. Where this bilinear transform come from? So let's go back to our basic derivation of this system. So the system in the discrete domain is x of k plus 1 is equal to phi of t x of k and psi of u of k. Okay. Now look, this phi and psi are some kind of a constant matrices. Now if you see in a way similar to what we have in the continuous domain, this is like x dot is equal to ax plus bu. Okay, and we know that A matrix is a very special matrix for the system, because the eigenvalues of A would be the poles of a system. So similarly, in this case, eigenvalues of this phi matrix are going to be the poles or of a discrete domain system. Okay, and this phi matrix is nothing but e to the power a t. Okay, so eigenvalues of phi or the poles of the system are going to get mapped to e to the power pole times t. You see that e to the power. So see, if I say eigenvalues of phi will be equal to eigenvalue of e to the power at, and if I know eigenvalues of a, then it will be simply e to the power eigenvalue of a times t. Okay, so the poles get mapped. So this is nothing but eigenvalue of a is nothing but a pole. Okay, so e to the power pole times t is going to be the new pole for discrete domain system. Okay, so pole for a discrete domain system is nothing but e to the power pole for a continuous domain system times sampling time t. Okay, so that is a basic nature here. Okay, so with this you can see that e to the power, so if I use s as a variable for the pole, then e to the power st is my pole for discrete domain system. Okay, so this is termed as z here or q here. Okay, so z is equal to e to the power st. Okay, and now if we simplify this in terms of its this exponential in terms of polynomial series expansion, you get some first and second order terms. Based on that, some approximation of the first order terms, one can now get this relationship, okay, which is termed as bilinear transforms. Okay, s is equal to 2 2 over t, this comes from that. Okay, so I'll leave it to you to derive that from that. So this has a genesis at a relationship z is equal to e to the power s times capital T. Okay, so the approximation to this relationship is gotten into for polynomial first order terms, collecting all the first order terms for the polynomial expansion, we get this relationship. Okay, so I would leave it to you to derive this relation. Okay, so now we'll see how do you use this relation for then implementation of filter or design of filters. That is what is our whole point of discussion. So we are doing this for finally be able to implement filter in the discrete domain or in our microcontroller. Now so these are like different ways to transform the system into one form to other form. So you can look at this, say for example you want to transform system to discrete domain. One can use backward difference formula or forward difference formula, or like you can take a transfer function of that system, and so this backward and forward difference formula will be applicable to the differential equation. Okay, so the differential equation operator d by dx will be approximated with this, or d by dt will be approximated with backward or forward difference formulae, and you can get the discrete version of the system. Or you can use the state space representation and do it by shift operator way. Okay, or you can use transfer function representation, and s, you replace that s by this value here. Okay, in terms of z, and you get like the z domain, or this can be also q domain. Okay, so both are very similar. Right now we will start using the terminology of a z domain. Okay, so for now we will not make much of a distinction between q and z. Both are similar kind of operators that we will consider. Okay, then these are the questions about mapping of the poles and zeros. How will this so these are kind of questions one can think about, ponder over and answer. We are not going to kind of get to them right now. So we will see right now, like main focus is for the filter. So this is, so once we have original system in S domain, any system in S domain, we are able to transfer it into a discrete domain by using these different kinds of transformations. Okay, that is what is a main crux here to consider. Once we have this transformation available, then it is easy to implement in a microcontroller. How we will see that in a minute. Okay. So this is what we are talking about, mapping mapping from S plane to Z plane. Okay, we saw that in terms of poles, it is like Z is equal to e to the power S into T. Okay, that is what is the mapping from S to Z plane. Now filter we need in mechatronic system for filtering the noise in the system. Okay, and to avoid the performance degradation when this noise goes into the feedback, then so typically filters are used to remove the high frequency noise, and the sources of noise you can have electromagnetic radiation coming from the fan, tube lights, and other kind of elements which are around the mechatronic system, or your motor itself will be generating a lot of electromagnetic signals which will act as a noise for your sensors. Okay, then we have we have some operations that are going on in the time domain. Okay, so what will happen with those operations in the frequency domain is another thing that we need to look at. Why? Because the filters have a role to play there also. Okay, what role this filter have to play? Say where we do this kind of operation differentiation is where, like say for example for your motor, okay, if you want to implement PD control, what you do, you take a value of your encoder and you use some kind of a difference formula, or you are differentiating that numerically, the encoder values, and getting your speed. Okay, so this numerical differentiation has some bearing on the noise. Okay, so it's very important to see what is happening with this differentiation operation in the frequency domain. So if you see differentiation operation like d by d t of a signal f of t, okay, if it is done, then Laplace transform of this d by dt of f will be simply like s into Laplace transform of the f, right? So so Laplace domain gives you this kind of a, like, multiplication of the original Laplace transform by s when you differentiate a particular function. Now if you replace this s by j omega, okay, so to kind of typically, if you remember, you have s is equal to j omega we use for getting a Bode plot of a system or getting a frequency domain response of a system. Okay, so when you use s is equal to j omega, then at that time, like, what happens is differentiation, if you see in terms of when s is equal to j omega, it's just simply multiplication by j omega to the original f of j omega. So f of j omega, or capital F of j omega, is our nothing but our signal content. Okay, so if the signal content is f of j omega, then the signal content for the differentiated version of the signal, okay, would be j omega times f of j omega, magnitude of entire of this thing. Okay, so one can see very easily, if your signal is a sin omega t, if you take a differentiation of this with respect to time t, then it becomes a omega cos of omega t. Okay, so you can see that when you differentiate the signal, the frequency content, okay, the frequency content would change, and it would change in a way that, like, it's whatever original frequency content, it is getting multiplied by omega. Okay, so so this of course is in the time domain. Okay, this is time domain signal. You can see here we are just observing this time domain signal to see what is happening in the frequency domain. Okay, it's not, we actually, if you want to kind of see this, ideally we need to take a Laplace transform or Fourier transform of this signal to say that, okay, oh look, the Fourier transform of this signal is indeed getting multiplied by omega to get a Fourier transform of this signal. Okay, so when it is differentiated, the Fourier transforms get multiplied by omega. Okay, so so what it means is, graphically one can say that, okay, if you have a signal here, okay, and you are using this differential operation here, so you differentiate and get a signal dy by dt here, and let's say this operation is some kind of a continuous domain ideal, differentiation that is happening. We are not really doing this approximation by using forward or backward difference formula or something like that. I'm just saying, okay, this is like a full differentiation. Then this differentiation operation would be this g of s will be s here. So this is like a transform that is happening, y of s coming here, getting multiplied by s, and then we are getting s times y of s as Laplace domain function, whose Laplace inverse will be dy by dt. Okay, so in the Laplace domain or in the frequency domain, this is simply getting multiplied by omega. Okay, this omega plotted on the omega axis will be like a 45-degree line here. Okay, so this is what will happen to this signal now is when it passes through this filter is can be seen here that this signal will become 0 here. It has value 1, it was there, that value when multiplied by this signal will become 0, and then at omega 0 there will be this signal has 0 value, and this has some finite value, but that will become 0, and then this is some kind of a response that we will get. Okay, so this is a differentiated version of a signal. Now so this is what the differentiation operation does to the signal, original signal. Okay, so one can see that if the original signal has some noise content now, okay, so it has some typically the signals will have a noise at a high frequency, okay, and when you pass it now to the differentiation kind of operation, okay, these are even if with the ideal differentiation, okay, you can find that okay, now this noise is at say omega n frequency, which is farther away from omega 0, typically higher frequency noise. Higher the frequency, that much is amplification for the noise that will happen here. Okay, so the noise in this signal will get amplified here. Okay, that is what is a main effect of operation of differentiation of the signal. And because of this, we need now filter to get rid of these extra peaks. Otherwise, your differentiated feedback is going to be noisy. In the PD control, especially, this is important because then the derivative part will get noisy, and you will not be able to use very high gains in the derivative operation. Okay. So this is how then you'll start off. You do this differentiation operation, and then you use a low pass filter to filter out this noise, and you get the filtered version of a differentiated signal. Okay, so this is how one can see what is happening in the frequency domain, and we use the filters appropriately to do the job that we want to reduce the noise in the differentiation operation. So sources of noise are not only whatever ambient sources, but your mathematical operations also can induce enhance the noise that is already there in the signal. Okay. So we have not yet talked about see, this is ideal differentiation, but if you have a forward difference or backward difference, there is some kind of a different kind of a form that will happen here, which we are not getting bothered about for now. Okay. So we just leave with this idea that okay, we are doing continuous domain differentiation, and we work with that kind of continuous domain system, and then say that okay, this is more or less similar to what will happen if the sampling time is fairly appropriate, and we are doing it in a discrete way. Okay. So the filter, if you see here, is some kind of a transfer function which has some kind of a frequency response or Bode plot, and then the signal passes through that, and it produces the output. Okay, that is a very simple concept of filter. So you see, this is like a first order filter here. Okay, so it has some kind of a cutoff frequency beyond which it has this tapering of some slope will happen here. You can have second order filter, or larger order filters will have this is a sharper and sharper cutoff will happen here. Instead of this going in a gradual slope kind of a fashion, it will go down fast. Okay, that will be a higher order filter. So when we have to implement this filter in the so we'll see how this filter can be implemented. So this is one of the ways of implementing filter is this moving average kind of a filter. Okay. So moving average filter will have a formula So what you'll do is like you'll at a given point you'll consider previous two or three or more samples and take an average of all those samples and keep it at that value. Okay, and you need to typically update the previous values of the sample, and we have seen that update can be done by using this kind of a way. So the one previous value will be current value, then second previous value will be previous current value. Like that we can go ahead and do the updates. Okay, these are the updates that we have seen when we implement like derivative control. We need to do this kind of updation of the previous value so that we are ready for the next sampling instance derivative to be completed in the next sampling instance. Okay. So we'll not worry about this frequency response of such a filter, but like one of the ways of implementing filter is like moving average kind of a filter. And if given a transfer function, then one can use this. One can use this. Suppose this transfer function is given 1 over tau s plus 1 kind of a transfer function. Then one can use s is equal to this bilinear transform formula and get that as a discrete domain transfer function, and using a discrete domain transfer function you can transfer it into the discrete domain time function. Okay, time equations. Okay, so how do we do that? That will be done by using this shift operator. So we'll stop for here for now, and I think some of these concepts, although you may find that they are kind of a little bit of tough to grasp immediately, you'll need to ponder over. You may need to go back and forth over the slides and listen carefully. Then you'll be able to grasp these concepts. I understand that these are like too many kind of different concepts are packed here together, but they are like done in a manner to kind of see that you are able to kind of develop filters yourself or implement filters yourself. But these are the ideas that you will typically need for the defined implementation of a given mechatronic system. Okay, because many times you will be bothered by the noise in your sensors, and when you further do this differentiation operation, your noise will further increase, and then you will get puzzled, okay, what to do in such kind of a scenario, how to kind of handle. That time these concepts are going to be very, very useful. Okay.